This video, we're going to introduce the basics of spectroscopy. We'll start off with a review of light, then talk about excited states and electron energy diagrams, move into molecular absorption, and then look at some actual UV-Vis spectra and UV-Vis instruments. In the next video, I'll follow up with some other spectroscopic techniques, taking for granted that you're good to go with everything we talked about in this video. Let's start off with a quick review of light. Light is more correctly described as an electromagnetic wave, meaning that it's a wave in 3 dimensions, and in 2 of those dimensions, we have an electrical field, and orthogonal to that, we have the magnetic field, and they propagate in a certain direction. And we can think of this wave, we can describe it as by its wavelength, which then we can directly convert to its frequency. Those are easily interconverted using the speed of the wave, and we interconvert these using the constant c, which stands for the speed of light in a vacuum. So c equals lambda nu, c equals wavelength times frequency. And then we can also discuss the energy of these waves, or really the energy of the photons when we think of it as a photon, a particle instead of the wave. And that energy is just going to be directly proportional to the frequency, E equals h nu, where h is also a constant, Planck's constant. This represents a standing wave, and if we're talking about electromagnetic radiation, we're actually talking about waves in 2 dimensions. We have the electrical component, which is represented here in red, but we also have a magnetic component orthogonal to that, represented here in green. So this is what propagating electromagnetic radiation would look like as a wave. You've done this before in general chemistry. If you've taken physics, you probably talked about it in physics. And this is going to be a lot like the last chapter, one of the last chapters that you did in analytical. This discussion is going to parallel chapter 24 in your analytical textbook, chapter 24, Introduction to Spectrochemical Methods. So, we can represent electromagnetic radiation as an oscillating wave with an electrical component shown here in red and a magnetic component shown here in green. For simplicity, we're just going to focus on the electrical component shown here in red, and know that there is that magnetic component to it. This is not solely a voltage. There's the orthogonal oscillating magnetic component, hence the term electromagnetic radiation. All right, so let's discuss the characteristics of this wave. We have the amplitude, which for electromagnetic radiation is going to be how bright. How bright is this? Okay, so if we suppose that this oscillating wave, the frequency and wavelength of this oscillating wave corresponds to red light, then that defines its wavelength and frequency. But how bright that light is depends on the amplitude, how tall. So this particular wavelength and frequency of light is getting brighter and brighter and brighter. Here's our original brightness. Or if we dim that light, so it gets dimmer and dimmer and dimmer, then we see the amplitude decrease. So we call this the amplitude. Now, the wavelength defines the frequency and the energy of the light. So, if we decrease the wavelength, like so, then we are changing the color of the light. So really it would be more appropriate to change this guy to something like blue maybe. There we go. We're changing the color of the light. We are also changing the frequency. As we decrease the wavelength, we are increasing the frequency, and we are increasing the energy. Energy is directly proportional to the frequency. All right, it's really important that you understand that when I play with the amplitude, I'm changing the brightness of the light. I'm changing the number of photons that are there. But I am not changing, I'm changing the amount of light that's hitting the substrate, but I am not changing the energy of the light. So amplitude is changing the brightness, but it is not changing the color or the energy of the light. All right. So at this shorter wavelength, we would say, oh, that's a higher frequency light. So I shifted from red to blue. If we go back there and shift back to, let me see if I can get back to red. And then if we were to go to longer wavelengths, then we'd be veering from the red into the infrared, lower energy lights. So longer wavelengths is lower energy. You can even kind of see it in monitoring this oscillation. As you decrease the wavelength, the frequency of this oscillation, the amount that this arrow is going up and down gets slower and slower. As you increase the wavelength, look at that guy go. It just seems more energetic. So short wavelengths mean higher frequencies, and it also means higher energy. Longer wavelengths means lower frequencies and lower energies. We can think again of light as its wavelength, its frequency, or its energy. You need to be able to pretty easily interconvert all three of those given the appropriate constants. Here's a nice little chart started by NASA and improved on by a couple Wikipedia authors, where they show the wavelength of a scale of electromagnetic radiation on the top there, and the frequency in the middle, and then the corresponding energy on the bottom. And we give different ranges of energies of light different names. Low energy light with very long wavelengths, you can see the wavelengths they're called radio waves, can be on the order of buildings or on the order of humans. So a few meters up to, hundreds of meters. And then when we start getting into shorter wavelengths, higher energies, we get into microwaves, then into the infrared, and then into the very tiny sliver of electromagnetic radiation that we can actually perceive with our eyeballs, the visible region. It's just a very tiny sliver of light in the universe. Most light in the universe we cannot perceive with our senses. We can't directly perceive it, so we rely on instruments to convert it to some signal that we can perceive. So when we get more energetic than the visible, then we are into the ultraviolet. And then if you'll notice on the line at the bottom, when we get into the from the visible to the ultraviolet, look at the energy there in electron volts. When we're in the infrared, visible, ultraviolet, we're talking electron volt energy. Energy is on the order of 0.1, 1, 10 electron volts. And think back about when we talked about bond energies with mass spectrometry. That's on the order of bond energies. And in infrared, you're certainly lower than the energy of bond energies. So we're not generally breaking bonds when we are lower than, not generally when we're lower than 10 electron volts or so, just as a rough guideline. And that's about into the ultraviolet range. If you look at that bottom axis, 10 to the 1, when we're up at 100 electron volts into the UV, we start referring to that light as ionizing. This is now ionizing radiation. We call this all electromagnetic radiation, but ionizing radiation means, oh my gosh, you do start to promote electrons and form dimers and potentially break bonds, and you ionize things when you are further into the ultraviolet, certainly into X-rays, and then into gamma rays. And this is problematic because it can be cancer causing, because if you ionize your DNA, that can be a very big problem. But also we need to consider that when we are probing molecules, if we don't want to break them, then we don't want to probe them with things that are putting out energies of, 100, 200, 300 or more electron volts. So in the infrared region, we're certainly being nice and gentle. In the visible region and in the beginning of the UV, we're being nice and gentle. As we go further into the UV and then certainly into X-rays, and we do use X-rays in forensic science to look at elemental composition, atomic composition, but then it's a little bit like ICP. We don't care at that point if we're breaking bonds and destroying bonds because we're just looking at atomic composition, okay? But you want to have a sense of wavelength, because wavelength for the UV vis range, because that's by convention, that's what they put the x-axis as. And then we'll get into wave numbers, unfortunately, for the IR. But the ultimate is energy. energy. What energy of light are we putting into these molecules to probe them and get some information about their properties? So here is a kind of trimmed down, a scaled down version in a table, much more succinct, where we're saying, okay, we have wavelength, wave number, and energy. In the mid IR, which is traditionally what FTIR is going to work, the wavelength is 2,500 to 25,000 nanometers, or 2.5 to 25,000 micrometers. But we tend to use wave number in that region, which I think is very unfortunate, but it's a fact of life. Wave number is pretty dumb, but it's just the inverse of the wavelength. Now the energy associated with this is going to be between 0.5 and 0.05 electron volts. And the kind of interaction you're going to have with the sample at that point is you're not even really messing with electrons. You're actually just sort of causing bonds to vibrate or bend or wiggle. You're exciting the bonds just a little bit. You're not near breaking them. It's very gentle. And we'll look at some animations showing that bond excitation. Okay, but you're not really even pushing electrons around. Then we get into the near IR region, which is used sometimes, not as much in forensics. Then we get into the visible and UV region, usually put together as the UV vis region, and that's going to tend to be from about 200 to 700 or 800 nanometers. We don't worry about wave numbers there. And here we're on the order of, look, below 10 electron volts, 2 to 7 electron volts. You're still not talking about breaking bonds for the most part in the visible and the UV vis region. That's in the ultraviolet region above 200 nanometers. But you are at this point exciting electrons. You're not ionizing yet. You're not throwing electrons out of the molecule entirely, but you're pushing them into what we call excited states. And we'll get into that a lot more later in this video. Then you get into this gray area between UV and X-rays, which we do not use a whole lot in forensics, but it does have some very good uses. People use this in mass spectrometry, actually, to ionize molecules. The vacuum UV, and those are wavelengths down to 10 nanometers, or energies of 10 to 100 electron volts. And at that point, you do tend to ionize molecules, kind of similarly to what an EI source would do. And then you get into X-rays, and then not only are you ionizing things by throwing out electrons, but you're throwing out electrons that are at the core of the atoms, core electrons, not valence electrons. And that's a pretty high energy interaction, but it does give you specific information about the atomic composition. All right, so we've done a nice review of light. Let's move into talking about excited states. What happens when you shine light and it interacts with the sample, usually by absorbance. And then corresponding what we're going to call electron energy diagrams, which are a little bit annoying, but you really need to learn them. Back in my day, they were called Jablonski diagrams, but it's more descriptive to call them electron energy diagrams. But they're going to be a good way to map out these different interactions that can happen within the sample. And then we're going to talk about the absorbance phenomenon itself. Okay, so we're going to do a real quick review of some very simple general chemistry concepts. When you started doing electron configurations in general chemistry, and this comes back in organic chemistry, you built on it. We're going to build on it here too. You said that, okay, when we have an atom, some of those electrons are going to be core electrons. They're going to be closer to the nucleus. They're going to be tightly bound to the nucleus in this core, and they're really not going to interact. If you think about all the chemistry you've done all these years, we're pretty much entirely talking about valence electrons. So now that we've mentioned those valence electrons, recall that those are the electrons that are in unfilled shells. Those are in unfilled shells. They don't have that 2 for the first core or the octet for the later. They're in unfilled shells. Those electrons are further from the nucleus, and it doesn't take huge amounts of energy to move them around. They'll move around, they'll interact, they'll form bonds, they'll break bonds. All of organic chemistry, all the reactions, and pretty much all the chemistry you've done has just been poking at valence electrons, just moving around valence electrons. And for the most part in spectroscopy, if we're going to mess with electrons, we are messing with valence electrons. This is particularly in the UV-Vis region until you get to X-rays, and then you're blasting at core electrons. Okay, oxygen's a nice example. 8 electrons total. 2 of those are core electrons in the helium configuration. And then we have 6 valence electrons. Look at something a little bigger like sulfur. Sulfur's got 16 electrons total. It's going to have 2 electrons in that inner core that are going to look like helium. And then it's got an octet in a second core, an outer core. And then it has 6 valence electrons left over. And again, those valence electrons can be moved around pretty easily, and you can form bonds with them and do reactions and things with them. But if you think about it, you never touch the core electrons. Pretty much all of general chemistry and all of organic chemistry, you never touched the core electrons. It takes a lot of energy to get down in there and mess with the core. Again, X-rays. We can get a little bit more specific here, and instead of just saying core and valence electrons, we can actually do the electron configuration. And you guys are great at this. You've done this a bunch of times. So for sulfur, we have 1s2, 2s2, 2p6, 3s2, 3p4. So the core electrons are the 1s2, 2s2, 2p6. The 1s2 is that inner core, and then the 2s2, 2p6 is the octet in that outer core. The 6 valence electrons are going to be the 3s2 and 3p4 electrons. Okay, now this is not rigorously correct. This is the Bohr model of the atom that we have here, but it's going to be a map, a way of thinking about things. Really, the quantum mechanical model of the atom is much more accurate. But those 1s, 2s, 3p, the numbers that come first, if you recall, we called those n, or the fundamental quantum level. So we can crudely draw this Bohr model where you have the nucleus sitting in the middle, and we draw these successive rings that represent the first fundamental quantum level, n equals 2, second fundamental quantum level, n equals 3, third fundamental quantum level. And as we go further from the nucleus, it takes more energy to move things from further to nucleus out, away from the nucleus. Now, the whole trick here with absorbance, or in general with photons interacting with matter, is going to be that the energy of that photon, the energy of that light, must correspond precisely to some transition within that atom, some transition. It can be, in the case of UV-Vis, it's going to be the transition between electron levels. Electron has to move from one level to another level, and the energy must correspond precisely to that level. It is quantized. When you guys talked about this in general chemistry, you talked about it in terms of the series. There was the Lyman series and the Balmer series that we've shown here, and you talked about the hydrogen atom as an example. So we don't need to worry about these series names. We don't really care. It's not that big a deal. This is kind of an astronomy thing. But what's important here, you talked about this ad nauseum in general chemistry with the hydrogen atom. You said, okay, there are these fundamental quantum levels, and if you give the right amount of energy that corresponds to one of these levels, then the electrons can jump up. They can get excited. They can move from a lower level, which we would call a ground state or a relaxed state, and that's where nature prefers to be. Nature prefers the ground state. Nature prefers low energy. But if you push energy into them and you cause these electrons to jump up, then they'll jump up, and then when they relax back down, they have to release that energy, and they can release it as heat sometimes. We'll talk about that in a bit. But they can also release this as light sometimes, and this would be emission of light. So here's the classic example for hydrogen. If you take a bulb containing hydrogen gas and you put a bunch of voltage through it, so you give it a bunch of energy, and that energy is able to excite the electrons in the hydrogen, kind of with that map that we saw previously, excite them up to higher electronic states, higher up to fundamental quantum states. And then as they relax back down to the ground state, they can emit light. So this is called emission. And as we talked about in lecture, you can't actually see. We see this purple. We see this mixture of light wavelengths. You have to put it through, in this case, they've got it through a prism. You have to put it something to separate it into its colors because our eyes can't perceive that mixture of colors. But when you do this, you get these very specific bands. Now remember, hydrogen is quite simple. Hydrogen just has one electron to push around, but you still get 4 different transitions. And these correspond to 410, 434, 496, and 676 nanometers. So we have a red, a green, a blue, and a violet. Now, if you convert, it's not a problem for us because wavelength is frequency is energy. We can go back and forth from one another. If you convert those wavelengths into energies, then that corresponds to the energy of those transitions between the fundamental quantum levels. Okay, now I want you to look at the way that the fundamental quantum levels are drawn in this picture. They're not drawn as circles like a Bohr model around an atom, like orbits. We don't really like to show the Bohr model. It's not rigorously correct. Instead, we've flattened out those lines and it looks like a ladder. It looks like a ladder, but this is just a representation of the energy of electrons or the energy held within an atom. And you can see we have 1, 2, 3, 4, 5, 6, 7 here. They get closer as you goes up. That's true. The energies tend to get closer, but it's like a ladder, and it helps us think. We're used to gravity, so the bigger the jump, the bigger the energy. So this is an electron energy level diagram. This is an energy level diagram, sometimes called a Jablonski diagram. This is how we are going to represent the energy of atoms and excitation of atoms. Here is an electron energy diagram for a certain atom that has, you can excite the valence electrons in the 3s up to 3p, 4p, 5p orbitals. And they've got the lines drawn in nanometers, but you can see the axis on the y-axis is written in actual electron volts. Now, this is just demonstrative. This is just a demonstration. We're not typically going to actually write out the energies in electron volts. We're not even going to give it an axis. We're just going to draw lines at different heights where the difference in the height represents the difference in energy level. So the longer an arrow you have to draw to say that it jumped from one level to another, that the size of the arrow is supposed to be directly proportional to the energy that you are representing. So the jump here from 3s to 3p is a big jump. The jump from 3p to 4p is a little bit smaller. The jump from 4p to 5p is not as big, but you can see we can also jump from 3s directly up to 5p. And then you can relax back down too. We could draw arrows indicating that something relaxed back down from the 5p or the 4p. And the energy emitted is supposed to be proportional to the size of the arrow that you would have to draw to indicate the electron or the bond excitation is moving up from one level to the other. So this is the electron energy diagram, and it's going to be a very useful tool for us to succinctly indicate excitation, typically with spectroscopy, inside of molecules and atoms. So we focused on atoms so far, and we do that because it's nice and simple. And we said, oh, look, the hydrogen atom, it gives 4 lines, it's nice and simple. But most of the time we are not focused on atoms, but things get a lot more complicated as even you get into multi-electron atoms, but most of the time we're looking at molecules, which are more complicated, even if we look at a really simple molecule. So we've got oxygen here. Now we've got 2 oxygens represented. Well, if those guys come together to form O2, this gets wildly more complicated. And the energy level diagram for this thing, for O2, gets more complicated than, much more complicated than for oxygen, for just O. And O has 8 electrons, and it has a lot more lines. Even the atomic oxygen has a lot more lines than hydrogen because it has many electrons. So this gets pretty complicated pretty quick. And the reason that we have things get more complicated, one of the biggest reason with molecules is when you got to organic, one of the first things you talked about is hybrid orbitals and molecular orbitals. So when atoms bond to form covalent bonds, their orbitals, that 3s, 2s, 2p, 3s, 3p, all that stuff changes, and you form hybrid orbitals. You form hybrid orbitals or molecular orbitals. So in that O2 molecule, it's no longer the electron configuration of that one oxygen atom. Now, in fact, you have core electrons within those oxygen atoms are untouched. They're not touched. The core electrons are untouched. But the valence electrons for those two oxygens have merged together to form molecular orbitals, to form covalent bonds. And one way that we could talk about those molecular orbitals, this is the way we're going to talk about it most of the time in spectroscopy, is sigma and pi bonds. Sigma and pi bonds. We said that those things form these hybrid orbitals, and they form sigma and pi bonds. They can put electrons in the sigma and sigma star state, as well as the pi and pi star state. So if you look at how you drew these molecular orbitals in organic, this looks a lot like an energy level diagram if we just pay attention to the middle. We have this kind of ascending ladder, and that's pretty close to how we're going to think about it. The lowest transition you can have, there's no openings. If you look at the sigma here, the sigma star, and then that second sigma, the pi, there's no openings in those. There's 2 electrons in each of them. And remember, that's how many you're allowed to put in each one, is 2 electrons paired with opposing spins. But if we look at the pi star has an opening. So the lowest energy transition to make here is to promote an electron from pi to pi star. And that is going to be the most common transition in UV vis spectroscopy, is a photon comes into a molecule and it excites an electron from pi to pi star. It's certainly possible to excite from that sigma to pi star, or even from sigma to sigma star, or pi to sigma star. But the most common is going to be pi to pi star transitions. So we get a lot more lines now in these energy level diagrams because we have molecular orbitals, and things get a lot more complicated. But we are looking at pushing electrons between these molecular orbitals. We're not in the UV vis region, we're not pushing them all the way out of the atom and ionizing things. If you push them to a really high energy state, they just fly away, and then you've ionized the molecule. If you push the electron very far from the nucleus, the electron is gone, and now you have a radical cation. We're not doing that. We can push electrons between these molecular orbitals and between these hybrid orbitals, bonding and anti-bonding orbitals, and they'll relax back down, and we have an absorbance event without any kind of ionization. Okay, things get more complicated still. And that is because when you bond 2 atoms together, in addition to, well, now you have core electrons, which we're going to leave alone except for X-rays, but the valence electrons have merged to form these kind of funky hybrid orbitals, molecular orbitals. On top of that, bonds are not static. We kind of teach you this a lot, to get you started in Gen Chem and Organic Chem. When we make models, we always make them with solid... we always make them with kind of solid tubes. When you guys make those models, they're always nice, solid, and rigid. The truth is, it would be a lot more like when you made bonds, instead of giving you those sticks that hold the 2 spheres together on either end, if we gave you a spring, if every one of those was a spring, I mean, that would be really annoying. You make this big molecule and it's sort of moving and bouncing around in your hands. That is a lot more like how molecules actually work, though. When they come together in a covalent bond, they vibrate. They can vibrate and have these funny vibrations because bonds really are a lot like springs. They're not a solid thing. So in the O2 molecule, we have these electronic energy levels that are the molecular orbitals that are represented in the energy level diagram. But it also turns out, even if we're not moving electrons, there is energy associated with that bond vibrating. The bond between these two this type of bond vibration we're going to call stretching. This is the OO stretching. And it turns out when we're looking at IR spectra, we are watching bond vibration. We are watching bond vibration. Now, this particular bond vibration doesn't show up in the IR. It does show up in Raman spectra. But you can see that they have a wave number associated with that stretch there, that 2061 centimeters or reciprocal centimeters. Again, wave number is dumb, but if we convert that to wavelength and then convert that to frequency and then convert that to energy, we would get a little tiny energy. It would be less than 1 electron volt, but there is some energy associated with the vibration of bonds. And we can also, if we put IR light into these molecules, that can excite this vibration. So in addition to exciting electrons to jump between these orbitals, we can also, with smaller bits of energy, excite bonds. And this excitation is also quantized. Okay, even though things got much more complicated when we moved from atoms to molecules, O2 is still pretty simple molecule. Most of the things that we look at in forensics are a lot more complicated than O2. So let's make it a little bit more complicated and look at something a little bit more interesting. Benzene. Benzene is a really nice place to start. And we'll start by just looking in real cursory way at the molecular orbitals of benzene. So we end up with a number of pi bonds in this aromatic benzene molecule. We end up with these 3 pi bonds. We also have the corresponding sigma bonds, and each one of those pi bonds is going to have a corresponding pi star bond. So now we actually end up with 3, and each of those pi bonds has 2 electrons in it. It gives us this nice aromatic compound, very stable compound. But each one of those pi orbitals has an energy associated with it in the energy level diagram, and then each of the antibonding pi star orbitals that are currently unoccupied by electrons, but that's where the electrons can jump to if they absorb a UV-vis photon. Each one of those has an energy level associated with it that we're going to represent in the energy level diagrams. So this is electronic excitation. We think about this when we think about, okay, well, I excited it with light in the UV-vis range, light with energy in the range of, 2 to 7 electron volts, or somewhere around there, real gentle. Probably actually even less than that. I can make I'm not going to break any bonds probably, but I can make the electrons jump between these pi to pi star or sigma to pi star or sigma sigma star orbitals, these hybrid orbitals. But just like we did with oxygen, we can push the electrons around with that energy in the UV-vis region. But we also have vibrations, and we got a lot of bonds in benzene relative to O2, and we got a lot more atoms. We got a lot more degrees of freedom, they call it. There's a lot more for it to wiggle. If you imagine making a benzene ring, again, instead of using sticks as the bonds, use springs. You can see there's a lot more wiggle there now. There's a lot more movement. So in addition to these electronic energy levels, we also have to consider, okay, there are a lot of vibrations going on here. So let's take a look at those vibrations. Actually, before we look at those vibrations, let's go ahead and look at a UV-vis spectrum that mostly represents. We will talk about how the vibrations fit into this spectrum. Now notice, this is a gas phase. This is benzene in the gas phase. That's going to become important later on. But we have wavelength on the x-axis. Remember, wavelength represents the qualitative information, and then absorbance, which represents how much you have on the y-axis. And the reason that we have these peaks corresponding to what the thing is because those peaks, if we convert them to energy, then those correspond to those possible energy level transitions for pushing those electrons from the orbitals they were currently in, the pi orbitals, up to the pi star orbitals, potentially with some of the sigma electrons jumping up to pi star, or maybe even sigma star, or pi to sigma star. But we have these electrons jumping from bonding to antibonding orbitals. And if we convert these wavelengths, peaks, into energies, then these energies, and that's what I've done here, that one at around 238 or so, that's about 5.2 eV, and then you get down to looks like 243 to me. I calculated that as 5.1 eV, 5.0, 4.9, 4.8 eV. those should correspond to the difference in those should correspond to the difference in the energy levels for jumping between for electrons moving between those bonding and anti-bonding, or those different molecular orbitals, the unoccupied molecular orbitals, the ones that have openings in them. This doesn't break the bonds. It's nice and gentle. It pushes them up and then they relax back down. It's possible that they emit light when they relax back down. Most of the time, they actually just emit heat. Okay, now let's get wild and watch benzene sort of wiggle around here. These are really cool simulations, by the way, by John Nash at Purdue. And you can see that they've modeled the bond vibrations, the different, they call them vibrational modes that we would expect from benzene, which is still pretty simple if you think about it. C6H6, and they're locked in this aromatic structure. But they show 9 different, what we would call stretches there. And each one they've written corresponding to a wave number. And we can convert that to a wavelength and then a frequency and then an energy. And that corresponds to the energy associated with those particular vibrations. But the reason they left it as wave number is we expect to see peaks around those wave numbers in the IR spectrum, because what you're watching in the IR spectrum is not electrons jumping around. What you're watching is, oh, I've put in a photon with an energy that happens to match this particular bond vibration or this particular bond movement, and that excites it. That light gets absorbed and goes missing, and that's read as absorbance in the IR spectrum. So that's one of the reasons that really the IR spectrum is so specific, is that you are actually probing the bond movements. You're probing the bonds instead of the electron energy levels. You're probing the vibrational energy levels, or you're probing the specific bonds. And that's much more indicative of molecular character. Now, when we do convert these reciprocal centimeters into electron volts, I've done that here. You can see that they're much smaller than, certainly much smaller than bonds breaking. And these energies do correspond to the IR region, as the reciprocal centimeters do, the wave numbers do. And the differences between them are really tiny. We're talking 0.001 electron volts. So the differences when you are watching bond vibrations, those energy level differences are much smaller than the electron jumps, which were the electrons jumping from bonding to antibonding orbitals in the UV-Vis region. We saw that those were on the order of 0.1 electron volts, or sometimes maybe a little bit bigger, but still, those energy jumps, even though they're 0.1 and that's electron volts, not small, that's 100 times bigger than 0.001. So the energy to jump electrons between molecular orbitals and things is a much bigger energy than these little vibrational energies. And so these happen in the range of infrared energy, which is much lower than visible or UV energy. Now we're going to draw a more complex, a little bit more realistic electron energy diagram. And hopefully you're not going, whoa, wait a minute. What are all these little lines? Well, just focus at first on E0, E1, E2. That's kind of what we were looking at before, where we are watching. Those are electronic transitions. Those are different molecular orbitals. So that is an electron jumping from a pi to a pi star, or from a sigma to a pi star, or something like that. It's jumping from a molecular orbital that has electrons in it to a molecular orbital that has space for electrons in it. But within each of those electronic energy levels, within E0, E1, E2, you see there are little jumps. There are those smaller lines, and that, if you look on the right, that's labeled 0, 1, 2, 3, 4. Those are vibrational excitations. Those are vibrational energy levels. Those correspond to that benzene wiggling, or that oxygen stretching back and forth. The arrows to jump between those, you see, are much smaller. So the energies to jump between those are much smaller. We've already seen that. to jump around in the between electronic energy levels, you're talking on the order of zero point 0.1 electron volts, and that energy corresponds to wavelengths in the visible and UV region. But to jump around between vibrational excitations corresponds to 0.001 electron volts. That corresponds to the IR. So when we see interactions in the IR, it's these little jumps between vibrational levels. When we see bigger interactions, when we see higher energy interactions in the vis and the UV region, we're actually pushing electrons into higher excited molecular orbital states. Now, the trick is this gets much more complicated because now we don't just have, oh, look, we have 3 or 4 electronic transitions. Within each electronic transition, we can have 4 or 5 vibrational states. And you can jump from the first vibrational excited state in E0 to the second vibrational electronic state in E1. So the number of possible arrows, just imagine the number of possible arrows you could draw on this page. And each one of those arrows is going to show up as an energy in the absorbance spectrum. So this all of a sudden makes it go from these nice crisp lines or these nice crisp peaks to a very complicated spectrum that honestly, when you're looking at UV-Vis spectra, ends up just kind of being big blobs because it's kind of too many lines for things to distinguish. So we've gotten through a basic description of light, and then we slogged through talking about excited states and electron energy diagrams. Let's apply some of that and actually start looking at data. We'll look at molecular absorption and what that entails, and then look more specifically at spectra for, we're going to focus on UV-Vis for the rest of this video. We'll get into FTIR and Raman in the next video, and then we'll look at some instrumentation for UV-Vis. So based on what we've discussed so far, we said, okay, well, we have these energy level diagrams shown in the bottom left there, that B part of the figure, where you can push electrons up to, from the ground state, which we've labeled 0 here, up to excited state 1 or 2. And we can look at that excitation in either terms of energy, or we can convert that to frequency, or most of the time we are going to look at it as wavelength. And that's going to give us the spectrum that you see on the bottom right there, C, where we have, okay, there's a peak at lambda 2 and a peak at lambda 1, and the y-axis is absorbance, representing how much gets absorbed, how much light gets absorbed. And what those peaks should correspond to are specific electronic energy transitions. Now, that's sort of true in real life, but we'll talk about how most of the time we work in solution, and solution sort of ruins that. I want to draw your attention to something I've taken a little bit for granted so far, and that is up top, the A part of the figure. We've really mostly been talking about absorbance. I talked about emission at the very beginning. That was atomic emission, where we looked at, oh, the hydrogen gets excited and then emits light. Most of the time, we don't use that in forensics. We don't use atomic emission. You can use emission to get atomic information about samples, but it's not nearly as good as ICP. If a lab really wants to do that, they're going to have an ICP mass spectrometer, or they're going to use X-ray methods that are also really good. So atomic emission spectroscopy is not very common in forensics labs. Absorbance is going to be really common, and then a scattering phenomenon called Raman, which we'll talk about more in the next one. But in absorbance, what you have happening is they've got it labeled as incident radiation P0, interacts with a sample. There are a lot of other things that can occur when you put light in a sample. It can be reflected, it can be scattered, it can just be transmitted intact. It can be refracted. But when we have an absorbance phenomenon, we put some light in, and then some of that light goes missing in the sample. It doesn't really go missing. Energy is always conserved. It just converted to a different form of energy than the light we put in. So we call that absorbance. And quantitatively, how we're going to look at that is we are going to compare the incident radiation with what's called the transmitted radiation. So the amount of light that went missing. We're measuring the amount of light that went missing and calling that absorbance, or absorbance is just another way of saying transmittance. They're not directly related, they're logarithmically related, but those two are a very simple conversion. Let's return to that cool standing wave animation to look at what happens if we put a material in the way of our light such that the energy of the electron levels in the material matches the energy of the light. Or we could say the wavelength, because wavelength is frequency is energy, right? So if we put this material in here and it's able to absorb in the path of the light, and it's able to absorb this particular energy of light because the electrons in that material, there's some energy transition level in that material that matches precisely the energy of that standing wave, then some of that light goes away. Now notice we are watching the amplitude decrease. Okay, the material is taking away some of the intensity of that particular energy of light. So as the standing wave passes through the object, it's not modulating the energy of the light, it's decreasing the amplitude. It's taking away some of the brightness. And this intuitively makes sense. If you're staring at a light source and you hold some material that, even if it's transparent between you and the light source, the light gets a little bit less bright. That's not always due to absorbance. It can also be due to reflections and scattering. But in this case, we are watching the amplitude of that standing wave decrease because the material, there are electron energy transitions in the material that match the energy of that light of that standing wave. Most of the time when we do these experiments, we're going to do them in solution, and we're going to use what's called a cuvette. That's not entirely always true. And remember, in GCIR, that's actually a gas phase infrared. There's no you're in the gas phase there. But most of the time, we're going to be in the solution phase, or in IR, you're just going to be a solid, the pure solid. But when we're doing UV vis, we're pretty much going to be in solution. We're going to put the solution in what's called a cuvette, and it's going to be plastic, glass, or quartz. Quartz is the nicest and the best. We have to very much consider some real things that happen between the incident beam and the emergent beam, or the light in and the light out, that have nothing to do with absorbance. And that is, you're going to lose light just because whenever you shine light on something, some of the light's going to be reflected. And that has nothing to do with absorbance. That's just some of the light was reflected off the glass, the plastic, or the quartz. But that is light that you put in that is now missing. And it can be falsely read as absorbance if we're not careful. Also, you're going to get a bunch of scattering. You're going to get a bunch of scattering. We'll talk about that more in the next movie when we learn about Raman scattering. But that's just light that is scattered in all directions and appears to be lost. Has nothing to do with absorbance. So we have to compensate for that whenever we do this with a UV vis instrument. Another practical consideration we have to have is that because in UV vis we are not dealing in the vapor phase, we are really usually in aqueous solution. And if we look here, this is a figure of this 1,2,4,5 tetrazine shown in the middle there in blue. A relatively simple molecule. In the vapor phase, it has kind of sharp lines, and we can trace those to electron and vibrational energy transitions in the energy level diagram. But the lines get blobbier when we are in a non-polar solvent in hexane. This guy dissolves in hexane. And then when we dissolve it in water, it's just one big gross blob. What is really happening here is that the energy level diagram is already pretty complicated, with not only the electron energy transitions, but also those little vibrational transitions within each electron energy transition. But then on top of that, when you have solution in there, you have something else happening. And those things are much stronger in aqueous solution than they are in hexane. So I want you to go back in your brain and think about general chemistry and think about what kinds of things could happen between molecules in water that are particularly strong interactions. Think about that for just a second. So if you thought, oh, he's talking about intermolecular forces, good for you. Yes. When you have these interactions with water, you can see this guy it has some polarity to it with the carbon nitrogen bonds. It can do some interactions with the very polar water. That actually shifts and makes even more energy levels, even more small vibrational. You end up with these rotational energy levels, they're called, and they shift because of the intermolecular forces, and you end up with so many of those transitions, so many of those little lines that the instrument just doesn't have the resolution to distinguish all these, thousands and thousands of lines, and it just starts to appear like a big blob. So this is the issue with UV-Vis spectra, is the peak are just big blobs centered around a maximum, and we do use that maximum for identification purposes, but it's pretty weak as an identifier. Let's look at some actual UV-Vis spectra. Now what you're seeing here is are UV-Vis spectra for potassium dichromate, phenolphthalein, and bromophenol blue. And then on the left, you can see on the top, there is that on the top, on the far left, it's just white light. They're just showing us, oh, that's white light. And when they separate it with what's called their monochromator, it separates out the colors. You see we have a beautiful Roy G. Biv there. And if you look one below it, that is what the cuvette looks like if you just look at it through white light. The potassium dichromate just looks yellow. Now, when you look at the light that's spread up by the monochromator just with your eyes, and we sort of I tried to show you an example of this in our Zoom lecture the other day, potassium dichromate appears yellow. Now, if we look at the, spread out light that emerges after the potassium dichromate, you see yellow is in there just fine. Potassium dichromate is not absorbing yellow. The yellow, the green, and the red pass through just fine, but what's gone missing is the blue and the violet. So you're seeing that yellow because that is the center of what is left. And if we look at the absorbance spectrum, this is verified. They've drawn it in yellow because it appears yellow, but look, it's absorbing the violet and the blue. It's absorbing very well below 400 nanometers. It's absorbing pretty well at 450 and decently at 500. So it's absorbing the violet and the blue light, and the yellow is the appearance of what is left over. If we look at the bromophenol blue, if we look on the left, we can see it appears blue when we look at it under white light. But that's because that's what's left. That's what's left. If we look at the monochromator output, excuse me, the sort of Roy G. Biv output from what's left over, we see that the blue is left over, a little bit of green, but the red is greatly diminished. The yellow, orange, and red is greatly diminished. And then if we look at the absorbance spectrum on the left, bromophenol blue is shown in blue, but in actuality, the peak is kind of in the orange region, and the yellow and orange is being very strongly absorbed, and a little bit of the red, but we definitely have that violet and blue completely left intact, a little bit of the red. So what you're seeing is you tend to see the complement. You tend to see the complement of whatever is actually being absorbed by that molecule. You are seeing the leftover light. That's what hits your eyes, not the absorbed light. Bromophenol blue doesn't absorb blue. It appears blue because it's absorbing the things that are not blue. Most specifically, the complement of blue, which would be kind of orange-yellow. Now, we all know phenolphthalein, that famous indicator, and it's kind of funny because it appears sort of a pink or maybe a purple. That's not a real color. That's a color that our brain makes up because phenolphthalein absorbs kind of smack in the middle of the visible spectrum. It absorbs the green and the yellow quite well. If you look at that, the peak is around, 550 nanometers, and it's absorbing that in that green-yellow region very well. The blue and the red are left over, and our brain combines those leftover lights to form that phenolphthalein color, but it's not real. It's just our brain saying, oh, that's a mixture of two very different colors. I can't tell you how that works. I don't know how that works, so I'm going to make something up. So phenolphthalein, when things appear kind of pink or purple, a lot of times it'll either be, if they're not a mixture, if it's a pure compound, it'll usually be sort of absorbing in the middle, and you're seeing the blended reds and blues. Now, if you start mixing colors together, then you can get all kinds of different colors. But then you're dealing with a mixture, of course. Let's take a look at a block diagram for a typical instrument. So this is going to be a really simple, what we call single beam UV vis instrument. This is specific now to UV vis. A lot of the stuff we talked about earlier with the electron energy diagrams and stuff, we're going to extrapolate to all kinds of spectroscopy. We could extrapolate to all kinds of spectroscopy, but now we're talking specifically about UV vis instrumentation. So you have to have a source. This is not an ion source like in mass spectrometry. You're not altering the sample in the source. This is just a light bulb. It can, if you're in the visible spectrum, it can just be a light bulb. A tungsten filament is a fine UV source, so that would be an incandescent light bulb. So this emits light. Now this is a broad mixture of light energies. So it has to go into, it says a filter, but for us, an instrument is typically going to be a monochromator. I'll show that a little bit later, but monochromator meaning one light. So this thing sorts the light into one specific energy or of light, okay? And then you're going to have the cuvette. Now, they say reference cell right here, and you see sample cell down below it, because before you get started, you have to run a blank. You have to take the cuvette filled with whatever solvent you're using. It's usually just going to be water or, some buffer or some acid or something like that. Remember when we did this the first week in making solutions, it was, I think, 5 millimolar HCl. You put that in the reference cell and you tell it, this is 100% transmission. Pretend that this is all the light coming out of the monochromator, hitting the photodetector. This is as much as you're going to get. This is 100% transmittance. So the light comes out, it hits the detector. The detector that we're going to focus on is the photomultiplier tube. For this arrangement of instrument is the photomultiplier tube. Okay, so you do that first. You set the monochromator to a specific wavelength. You have to scan. So let's say you set it to, I'm going to start at 200 nanometers. So you turn on the UV source. The monochromator only lets 200 nanometers through, or if you're going to have a really high resolution monochromator, you could say, okay, this is going to be 200.00, and then I'm going to switch to 200.01, but we'll say 200 nanometers. You have the reference cell in there. The light passes through and gets converted to readable electrical signal, so voltage or current. And then you tell the computer, okay, that was 100% transmittance. That was all the light that you're ever going to get at 200 nanometers using this system. And then you switch to 201. Or if you're going to be higher resolution, 200.01 and then 200.02. You're going to scan through the wavelengths. And you're telling the computer each time, okay, this is the maximum light you're going to get at 200 nanometers, 201, 202, 203. And then you have to, you've zeroed out the instrument. You've used that blank to tell it what zero was. And then you pull that cuvette with just a solvent in it out. And then you replace it with the sample cuvette. Or you can clean that one cuvette and put the sample in it. And then you put it in. And then it compares the signal for, it sees how much the transmittance goes down, how much light was absorbed, how much less light was transmitted at each wavelength. And that is what it is plotting in the spectrum. Now, that kind of instrument is not super common. You saw me use a UV-Vis instrument with one cuvette in the making samples lab, but that's actually a little bit different kind of setup that we'll discuss later. The scanning setup, it makes much more sense to do what's called double beam, and this is going to be the most common instrument that you run into in forensics labs if you're still seeing a UV-Vis instrument, is a double beam scanning instrument, because it has good sensitivity, and it has good resolution, but it's really slow. Now, it's the same idea, except instead of constantly switching out, oh, my blank and my sample, instead of constantly switching out your blank and your sample, the double beam has two holders for two different cuvettes. And the one in the rear, the one in the back, is always the reference by convention. And you just put your blank in there. You put your reference, just a cuvette, the same type of cuvette you're using for your sample, with the solvent in it. And then you put your sample in the front one. And then the blanking is taken care of automatically. You see there's a motor and what's called a sector mirror there. And essentially what it just does is it's constantly switching back and forth and measuring, okay, blank sample, blank sample, blank sample, blank sample. It just constantly switches between those two things as it scans from 200 nanometers, 201, 203, 204, all the way up to 800. It constantly switches back and forth, back and forth, back and forth. This gives you better data because if there's slight fluctuations in the instrument, those fluctuations are going to occur to both the blank and the sample at the same time, but also it's just a lot less annoying. You don't have to sit there and blank the whole spectrum and then remove it and put in your sample. You just plop both in there and punch go, and it does it for you. So this double beam scanning instrument, if you have a scanning UV-Vis instrument, this is going to be the most common configuration, where you have this sector mirror, or sometimes called a chopper, that swivels, and it sometimes it actually physically turns in a circle, and when the mirror part hits, it beams up through the reference cell, and when it's transparent, it passes through the sample cell, but it just forces it to constantly switch from blank sample, blank sample, blank sample, blank sample. So it's a constant comparison, and you only need one detector because the detector is seeing the difference between the blank and the sample at all wavelengths. Let's look at an actual instrument schematic, a little bit more detailed schematic. And this is actually the Carry 100. This is the instrument that we have up in the lab upstairs. You probably never even noticed it. It's over in the corner of the instrument room. Now it has, they say, tungsten and deuterium source. The truth is you have to have two light bulbs because the tungsten light bulbs are not UV sources. They don't give you UV light. Deuterium lamps give you really good UV. So you have to have both. And actually, when you switch at about between 350 and 400 nanometers, when you switch from the UV to the visible region, you hear a click in the instrument, and it's actually switching. It's switching over to the other light source. It's uncovering one light source and covering up the other one. Now, just like we had in mass spectrometry, you have to have optics, but they're not ion optics anymore. They're photon optics, or what we're used to thinking of as optics. But just like in mass spectrometry, light loves to scatter. It loves to fly all over the place. When you have a light bulb, it's not just focused in one direction. It's blowing all over the place. So you have to take that light that's blowing everywhere. You have to get it sort of pointing in one direction. That's called collimating. So you're going to have optics that are called collimating, and that can be either a lens or a mirror. A lens is going to be the light passes through it, and as it passes through it, if it's a collimating lens, as the light passes through it, it's sort of pushed in one direction instead of just shooting in all 360 directions. It's forming a nice beam. A collimating mirror would be the light bounces off of it, and as it bounces off, it forms a nice beam. There's also focusing. There's focusing, and this is going to, instead of bringing the light into a nice beam, a nice formed beam, it's going to focus it to a specific point. It's going to have what's called a focal length, so it focuses to a specific point at a specific distance from the lens or the mirror. Again, you can have focal lenses or focal mirrors where the light can pass through the optic in a lens, or it bounces off, it's reflected off of the optics for a mirror. So a nice common trick we're going to use in optics when we want a nice beam is just a slit. That's just, really, you can do this with black paper and a razor. I mean, really it's done with metals and very carefully cut metals, but black metals. But essentially, if you're shining a light on something and you have cut a very tight slit, then that light's going to tend to form in a beam through the slit. It's just making a little window for the light to pass through, and the rest of the light just doesn't make it, so you get a nice beam. Then you can see this goes into a collimating mirror that's going to take that beam and keep it as a tight beam. And then it hits the grating. And the point of the grating, as we saw in that Zoom lecture, is to spread the light into the separate wavelengths. The grating is at the heart of the instrument. And then those wavelengths hit a focusing mirror. Now the trick is that focusing mirror can rotate a little bit. That's going to focus the light, but it's also going to focus one specific wavelength onto that slit. So this arrangement, the first slit, the collimating mirror, the grating, the focusing mirror, and that second slit, that is the monochromator. In the previous block diagram, we just sort of represented that as a block. But now we're seeing, oh, this is how it actually does it. It pulls in white light, collimates it, and then the grating spreads it into the different wavelengths. And then that focusing mirror focuses one specific wavelength onto the slit, so that onto the exit slit, the one at the bottom there, so that only one wavelength of light passes out of the monochromator. So it is the monochromator, meaning one wavelength, one light passes out of that thing. All the light wavelengths go in, only one specific wavelength comes out. And then we have a series of mirrors. The reference in the sample with that chopper, as they call it here, they called it something else in the previous one, but really it just spins back and forth and makes it alternate sample reference, sample reference, sample reference. And the detector here is what's called a PMT, or a photomultiplier tube. Let's look a little bit more at that detector. It's going to look pretty familiar. So a photomultiplier tube is a vacuum tube with a series of plates. Here's a nice picture by Hannes Grob. Let's look inside and see what it looks like in a schematic. Okay, so here we have a process called scintillation. This has been known to us for a very long time, and that's, you can take a higher energy photon and you can have it impact a material and convert to lower energy photons. And then when this lower energy light hits what's called the photocathode here, it's just a material, this is really common, that converts photons to electrons. So when those lower energy photons strike the photocathode, you get an electron or a few electrons. And then this is actually focused through kind of a little ion optic there into a series of metal plates. And with each metal plate, that electron causes the release of more electrons from that, and it amplifies it. It causes this electron cascade. And this should look this part should look very, very familiar. Think about, why is that familiar? Oh, I have this electron and it hits a plate, and then more electrons come off that plate, and then that even more electrons come off the next plate, and more. That's because that's an electron multiplier. That's what we did in mass spectrometry. So basically in the photomultiplier tube, we take the photon, we convert it to a lower energy photon and then an electron, and then we just put it through an electron multiplier, and we get a signal with good gain or good amplification. So photomultiplier tubes are pretty sensitive. They're really good detectors for these double beam instruments, but we're going to talk about a different configuration of detector now that's honestly not as good as a photomultiplier tube in terms of absolute quality, in terms of sensitivity and the performance that goes along with the double beam instrument, but it's much, much faster. Okay, so if we look at this schematic, this is fundamentally different. We have our light source, we've got some optics going on there, but then we are shining the entire light output from the source. So if this is a visible instrument, we're shining the white light through the sample, all of it through the sample, instead of just one wavelength at a time like we did before. So that's already a little bit wild. And it's going to the thing there called the spectrograph. That's really just a series of optics. It's going to be similar to the monochromator where, okay, we come in, we have a collimating mirror, and then the G stands for grating, and that spreads it out into all the wavelengths of light. And then we have another collimating mirror, but all those different wavelengths, they're at different positions, but they hit that thing A. So the light colors, the wavelengths are spread out to different positions, and they hit this detector. But the trick is the detector is going to be a position-sensitive detector. So it's going to know that, okay, the red is on the right and the violet is on the left, essentially. And that's called a photodiode array. We'll look a little bit more closely at that detector. Okay, so here's again a specific. We don't have this instrument, but we do have several photodiode array little instruments. I used a photodiode array instrument to look at your making solutions stuff the first time. They're going to be a single beam instrument, but it's kind of a different phenomenon. So here we have the tungsten and the deuterium lamp here. This is actually UV vis, so they're putting not only white light but also UV light through at the same time. They have a filter or a shutter in there that most of the time is just going to stay open. All of that light passes through the sample, passes through the cuvette. There's a lens to collimate things. There's a slit to make it kind of a nice bend, a nice beam, sorry. And then it hits the grating. But when it hits the grating, you see all those different wavelengths are spread out spatially. They're spread out in space. So, you know, you get that rainbow effect where the Roy G. Biv and actually the UV are all spread out from each other. And then it hits what's called an array of detector. This is not one detector. This can be tens, hundreds, or potentially a couple thousand detectors that are lined up next to each other. And each one of those detectors, so detector number one, you calibrate it so you know what spatially, you hold that photodiode array in a specific position. You know, okay, based on these standards, the one on the far left, photodiode number 1, 200 hits that, and then the one right next to it, number 2, 200.2 hits that, and the one right next to it, detector number 3, 200.4 hits that, and all the way up to detector number 2000. These are essentially pixels. This is a lot like how the camera in your phone works. These are essentially pixels. It's an array of pixels, and you just know what wavelength each pixel is supposed to correspond to. So photodiodes themselves are really cheap. Have you ever seen like actually a kid's toy where if you move your hand in front of it, like my kid had this toy where it was a puzzle, and if you there was a chicken that fit in there, and if you picked up the chicken, then it would go bonk, bonk, bonk. And if you looked, there was a photodiode in there, and it was when the light was blocked, the photodiode current was low, photodiode voltage was low, but when you lift it up, it sensed the light, and the voltage goes high, and then it plays the chicken sound on a speaker. So you may have run across these like children's toys, or you've almost certainly seen photodiode in everyday life. Things that are sort of simply light sensitive are usually photodiodes because they're very, very cheap. This one's $8, which is actually kind of fancy. They're usually like $1 a piece. So an individual photodiode is a real cheap, simple little transistor. Because they're cheap and because they are small, it's not a big deal. And this is not a really big photodiode array. So what you're seeing here, this is a chip from OSI Optoelectronics. And this, you can make them smaller than this and put a lot more in there. If we count each one of those pins, see each one of those pins corresponds to an electrode on one of those photodiodes. Looks like there's about 30. And if you look closely, you'll see the kind of individual rectangular pixels. Each one of those pixels is a photodiode. So there's like 30 photodiodes there right on that chip. And that's not even a lot. Like I said, it's not that big a deal to buy a photodiode array that has a couple thousand diodes in it. But there's definitely a discrete number of detectors. There's a discrete number of diodes you have to know. And that's going to limit your resolution because you can essentially only have, I have 2,000 photodiodes, so I essentially have 2,000 pixels. That's going to limit your resolution. You are not going to get the kind of resolution that you would get in a double beam scanning instrument. But this is actually cheaper than a scanning instrument, even though you have all these photodiodes. And photomultiplier tubes are awesome, but you're not going to take an array of 2,000 of them and put them together. So these are inferior detectors to photodiode arrays. Inferior detectors to photomultiplier tubes, except they're awesome because you can make this giant array of them, and you can have all the light hit them all at once. And what's great about this is it can be cheaper, but also it's fast. There is no scanning. So why do we care about fast? Well, the truth is, back in the days where we had scanning-only detectors, you had to just park the UV vis at one wavelength. You really couldn't scan because it was too slow if you wanted to use it with an HPLC. And this is the most common detector for HPLC is going to be UV, or if you can afford it, mass spectrometry. But UV, you might as well get it when you're getting an HPLC because it's real cheap. So I've drawn a real simple schematic here where you have a broadband UV source, and then you just have a simple, they call it a light pipe, where the flow in from the column goes through a path length or a special sort of turn where it gives a chance for the light to pass through the sample. That goes to a diffraction grating that then shines the light on that photodiode array. And because you have all those pixels there, the different wavelengths hit at different points along the photodiode array. So you almost instantaneously get the entire spectrum. You are not scanning like you would in that double beam scanning instrument. You're not going, 200, 201, 202. You're getting the spectrum very, very quickly. And that's really important because when you're doing chromatography, it's all about how many data points can you get across a peak. If you're not moving fast enough, if you don't get enough data points, then you're going to miss peaks or you're going to distort peaks. So you got to be really fast. So the photodiode array is awesome for HPLC because it's fast. And this is, except for a very, very specialized HPLC system, in pretty much every modern HPLC system you see, when it has a UV detector or a UV vis detector, it's going to be a photodiode array. A lot of times now they just say, it's a PDA. And you'll be like, you mean a UV vis? And they'll be like, no, it's a PDA. But what they're saying is that is a UV vis detector with a photodiode array detector, so that you get that rapid full spectrum. So if you go back to the HPLC video, which I would encourage you to do, you can look at where I show you, oh, if you click around, you have this three-dimensional data. We showed that very specifically for mass spectrometry, but now you can go back and look and you get the full UV-Vis spectrum. It's not as descriptive as a mass spectrum by far. It's a big kind of blobby peak, but still it does give you some pretty good information, particularly for compounds that have color to them or have some more conjugation, something like LSD that has extra conjugation to it. We'll talk about conjugation and absorbance spectra in a Zoom lecture. But you get the full UV spectrum when you do HPLC with these photodiode arrays. All right, so we started off with some pretty broad concepts talking about light and electron energy diagrams, and that's going to apply to all the spectroscopy that we do. Then we focused a little bit more on molecular absorption. I threw some IR in there, and IR, those vibrational bands do influence UV-Vis spectra, but we focused in the end very specifically on UV-Vis spectra and specifically on UV-Vis instruments. And we essentially said, okay, in the forensics lab, if you want a really high resolution, more sensitive instrument, you're going to use a double beam scanning instrument. But then in HPLC, when you just need it to go real fast, you're going to use a photodiode array system.